I'm a computer engineering major, undergrad student at Utah Valley University. This work is exploration of object detection via low-cost autonomous drone. The work was done with the EC Machine Learning and Drone Laboratory on campus. So, to get started, I want to talk about.
There's another one.
There is. This is the one that works.
Yeah, go old fashioned.
Okay.
Old fashioned.
It was working before.
Yeah.
So, to get started with, I want to talk about. Oh, it did work. It just had a delay. So I have to go back. All right. So let's talk about the big picture and the purpose of what we're doing here. So, the goal of this is to create an automated drone system for wind turbine inspection. We are gonna basically try to figure out which of two path planning algorithms are more efficient. So the idea is if you have a drone that you want to use to inspect the turbine, you can send it the coordinates, the latitude and longitude, for the drone to travel, over a distance of miles. And if it gets there and it doesn't see the wind turbine, you're gonna have to do an exploration algorithm to be able to find the wind turbine when you know it's in the vicinity. So we want to demonstrate this in an offline solution. So there's no GPS on the drone we're going to be using in the experiment. And another reason, a big reason of why we're doing this is energy expansion. We're going to be demanding more renewables in the future. They're going to be a big part of our future. They are very costly to maintain in terms of both labor liability and the time energy production is offline. So to inspect wind turbines, what's needed to be done is these wind turbines need to be they need to be stopped. So in order for someone to climb up with a rope and be able to manually inspect the turbines, there's downtime of the turbine. It can't be spinning. During this time, this period can be months long, and that is, for all that time, we're losing energy. So the cost of that is really great. There's also a risk associated with it when you have people climbing up a very tall structure. There is a new way of inspection. This is done via drones. Some companies are already doing this. They fly drones out to inspect and take pictures. This is done manually with someone using a drone controller, and the pictures after they're taken, they're going to be manually inspected to see where the damages are, if there are any. The difference we're trying to do is we're trying to make it automatic, in which the drone already will just fly to it on its own without any human input, and the images are going to be we're going to be using a machine learning model to determine whether there are damages. So that's one of the phases of this project right now. What we're focusing on is the path planning part, the area exploration. But that is the goal in mind we have. We are going to do a small scale proof of concept. This is because using large wind turbines and large drones are very expensive. So what we have done is we've replaced fans with fan pedestals, and instead of using the large commercial drones, we've used these very low cost quadcopters from DJI Tello. The one you see up top here, this is the Tello EDU, which has a bottom facing camera that we use for landing on a helipad. This one right here is the same thing but without the bottom facing camera, so it has that less feature, but they both have a forward facing camera that we can use for image processing. So we programmed these drones using Python. We use a combination of DJI TelePy library as well as OpenCV, which is a really good open source package that's used for image processing. We do have the lab on campus, but note that we actually did a lot of the experiments in the CS atrium, a really big space. We had to do these experiments many Saturdays in this space right here because the drone lab actually isn't big enough for what we want to do. We needed a large space, but we didn't want the interference of other students, and we don't want to disrupt classroom times because these drones, as small as they are, make a lot of noise. So we wanted to use the atrium of the CS building. We are going to be implementing object detection and detect fans, and we're going to be using QR codes that we put on the fans for target verification. So the drone is required to consistently and reliably track its Cartesian coordinates. We have an algorithm right here. This is some pseudocode of what we use. So when the drone, wherever it takes off, that's what we call 000, that is the origin. We give the drone an X target and a Y target to travel to. This algorithm, what it does is we can calculate the angle at which the drone should rotate in order to face its target. And we also calculate the distance the drone needs to travel in order to get to the X and Y target. An example, I can explain this part right here. This is the distance calculated. If you have the drone's current X and Y coordinates and you have the X and Y target, we can just calculate the distance to travel with this simple equation, which is the difference of X squared plus the difference of Y squared. We get the square root of that to get the distance. So as the drone is moving, we're continually tracking how much it's traveling and its new coordinates after it's done moving. So with when we program these drones, we give it commands to move a distance in centimeters. It's not entirely accurate because the drone could shift due to drag, wind currents. So even though the drone thinks it's somewhere, it could be somewhere just a little off. And we're gonna be using object detection to help with this, which I'll explain later. The different flight algorithms we're gonna be going over are the snake path, which is also known as the keeping path, and the spiral, also known as the square pattern. So these both start at the same location with the drone right here, and they both end with the drone going back to the starting point after it's done exploring. These red arrows represent the direction the drone is facing as it moves along. So the difference is that the snake path goes from side to side, the spiral path goes radially inward. So, and this is the experiment layout. We have tape on the floor for reference. The drone is not actually following those tape lines. This blue represents the snake path, and then the white tape represents the spiral path algorithm. So that's when we have the drone fly, we're gonna be just comparing it to the tape to make sure that it's following the path. It is only for reference, it doesn't follow it. And we are gonna be measuring how efficient these two paths are based on two factors, on the battery consumption and the time it takes to travel its path and search the area. These are the algorithms we use. So right here, we're not actually telling the drone to go forward this many times and then turn left this many times. We actually have algorithms for this, so it's encased in a while loop, so we can easily adjust the parameters of the X boundary we want to explore, the Y boundary we want to explore, and the distance in which we want the drone to take a step. So we can actually create different sizes and varieties of these exploration patterns just by simply adjusting a few variables like the X max, the Y max, and the distance we want the drone to take a step. So it's fully adjustable with different variables that we can change. An example, we also have a Boolean for the snake path. This determines if we want to move clockwise or counterclockwise, because sometimes we want to move counterclockwise and sometimes we want to move clockwise. So we have a lot of Booleans and variables that determine what's the next step in the path to travel. And so we ran 10 tests for each different pattern, and we wanted to see which one would be more efficient, which one would finish faster, and which one would use less battery. And these are the results. Right here, there's usually a sharp decline in battery life when the drone initially takes off, but that seems to stabilize after a moment. It looks like steps because when we ask the drone to tell us its battery, the drone gives it gives us a rounded number, so it doesn't give us decimal points. That's why it's not a nice smooth curve. But the results we have are right here for both. What seems to be the case is the snake path uses less battery, and that's probably due to the fact that it finishes faster with that path that I showed you. So right now, what we're getting at is snake path seems to be better for area exploration, but the next step is to actually add these targets which act as wind turbines. So we, to detect them, we trained a hard cascade classifier using many images of these fans to be able to detect it. We use OpenCV's cascade classifier method, which runs a hard cascade detection algorithm. And what that does is it'll put bounding boxes on the images. We process the images with OpenCV. We get these bounding boxes, and what our function in Python does is it returns the size of the bounding box as well as where the bounding box is within the camera frame. So both of these pictures are from the drone's camera. If we have the size of the bounding box and we know where it is on screen, we know if the drone, we can tell the drone how much to rotate to face it, and then we can tell the drone how much distance to travel to meet that fan. So when the drone does detect a fan, what it does, it'll center its view to align the bounding box to the center of the camera frame. Then it'll travel a distance to get to the front of that fan and then lower its altitude in order to scan the QR code. These QR codes don't actually aid in exploration, it's only for object identification, which I'll explain in a moment why we need that. So right here in this instance, this is wind turbine 3, and we have this identification right here that the drone can recognize. So when the drone does scan a QR code, it returns back to the exploration pattern it was right when we saw this. So this would be an example of using a snake path with the orientation of 3 pedestal fans. So the drone would start right here and make its way through here if there were no fans. But since we have fans, and the drone is gonna see this fan as soon as it takes off, it's gonna be within its camera frame. So what the drone will do is it's gonna approach it, scan it, and then go back to where its location was previously in the path and continue forward. These little symbols right here are showing what direction the drone is facing. When the drone scans a QR code, it does make a small no-fly zone around that area to avoid collision, because it does fly at a height at which it could collide with the fans. So for example, when it gets to here and faces forward, it can see target 2, so it'll fly to it, scan its QR code, and then continue on the exploration path but go around it. And at this point right here, when the drone is facing down, it's gonna see target 3, approach it, scan it, but instead of going back to the path to finish, the QR code tells it that it found the 3rd target, so it can go back to the origin. So the QR codes are used to show that the drone didn't just find the same fan. This is a unique fan that has not been found yet. This can tell the drone when the mission has been finished. And this grayed out part, this part is grayed out because the drone shouldn't have to travel that if it already scanned the fan. It should just go back to the mission since it knows that all were found. So we wanted to make multiple test cases in which we have fans in the same positions for both the spiral pattern and the snake pattern that are demonstrated right here. We have 5 different cases here. So the right, we have the spiral, and on the left we have the snake path. We purposely put some fans outside the exploration pattern to really put the drone to the test. And we wanted to measure we wanted to calculate what a successful flight is by these parameters. So the drone has to take off at the starting point and return to it at the end. Detect all 3 fans and their QR codes with no outside interference, and traverse the area exploration as expected without deviating from the path. With the exception of if it found all fans before it finished the full path, then it's just gonna go back to the origin, since there's no point in searching when you know that all have been found. So again, the point of this is to find which one is more efficient to find fans in an area when you don't know their exact location. These are our results. The top here is for snake path and the bottom is for spiral path. So the results seem contradictory to our previous results when there was no fans and we didn't use object detection. The spiral seemed to do better as it was able to have better battery depletion. So this is not the battery life that's remained, this is how much that was depleted. So smaller number is better. And then the flight duration is also lower than in the snake path. It's believed that this is due to some cases where the fans are on the outside. So if you have a spiral path, they're gonna go around the perimeter first, and if the fans are close to the perimeter, you're gonna find those first. Where snake path would excel is in cases in which the fans are closer to the center of the search area, since the snake path goes through that area first, and the spiral path would reach the perimeter before it goes to the center, since it moves radially inward. So that's our reason for believing the spiral path does better when we introduce object detection and actual targets. So what this tells us is if we don't know exactly where our targets are, snake path should be a better exploration algorithm. But if we do know where the fans are and we suspect that they are going to be closer to the perimeter, a spiral path algorithm would lead to better outcomes, since it would go for the fans outside the perimeter first. So those are the differences between the two. They're both good, but they just have different uses depending on what your situation is. The goal of this was to see what is more efficient exploration when turbines aren't found. So even if there was GPS, we knew the locations of the fans. When we travel to it, if we don't see it, we need to find it, because GPS can only be accurate to a certain measurement. GPS is used to get to the area, the vicinity. We know there are turbines, but we may still need exploration. And these are the results of those two patterns. So I'm not sure how I'm doing on time, but I
You did
think
great. So I did a little bit of cheating yesterday. I told the angel to go for 15 minutes and he just did that 15 minutes. So anyway, so we have time for a couple of questions.
So when this is scaled up to full wind turbines, how will you identify which turbine's which? Like instead of a QR code, what will you use?
good question. We probably may not be using, we could use QR codes, but we might find another way to verify what it is. In a real life setting, these turbines might actually be more spread out more. So if you know you're in the vicinity of a specific turbine and you find a turbine, it's likely to be that one. The reason we had different fans is because we wanted to see how it would correspond in different locations within a vicinity. Like we have 3 fans per each case because we didn't. If we wanted to test many locations, we'd have to have a lot more cases, a lot more tests than we were willing to run.
So, looks like your algorithm that you had was based on CCM, previous CCM, and then but you used the 2D, it was pretty much two-dimensional. So you could have.
Yeah, there's another variable of the z direction, but the fans are usually going to be they're at the same height, so we didn't adjust the altitude. We only adjust the altitude when we want to scan the QR code.
Is there any way that you could make a path that's more optimal than the snake or the spiral, depending on if you already know the data of where the basic vicinity is? Could you make like a path that would be more, just more optimal than either of those?
So what kind of paths are you thinking?
This one that would be generated where it goes from where one turbine might be to another where it might be, and then it would.
Well, we don't know exactly where the
Exactly.
turbines are. I mean, with either path, we can say the turbine could be here, or maybe I'm not understanding your question fully.
Maybe if you just
Are there other optimized paths other than this?
yeah, like
I mean,
yeah, or like ones that you could generate if you know kind of where a wind turbine is, or if that kind of makes sense. You might not know that it's right here, but within this certain radius, it is here, so
Yeah.
you could have the drone go to that point, and then another point, and
Like-
then some other point.
like there's different probabilities of where it could be within this area.
Yeah.
Yeah, but there's, I guess, different probabilities of where it could be. This is kind of like a one size fits all, where it's just going to explore the entire area, and if it finds it sooner, then better. But if there's a higher probability of a turbine being somewhere, then we would just start the drone at a different location. You can just start it closer to that and then search it.
Okay.
But I would just say if we could just move the drone, I guess, closer to the more probable location, and then just do the exact same thing we've been doing, which is one of these two.
I believe there were 2 more questions here.
So the drone you're using only has a forward-facing camera and maybe a downward-facing one?
Yeah,
Is
the
that
downward
correct?
facing is what we use to land on the helipad.
Yeah.
So it's able to finish where it starts. If we actually just use the white drones, which don't have the bottom camera, and we tell it to land on the helipad where it starts, it'll actually be a few feet off because, even though the drone's keeping track of its course, it's not super.
I guess my follow-up question to that is, have you considered that it might be more optimal to go to a single point and then rotate so that you can see in all directions, and then go to another point and rotate again so that you can see in all directions? And would that potentially be faster or consume less battery in traveling?
So the thing is, when we take, I should have probably mentioned this, when we take images, we're not actually taking images when we move, we take images at each step we take, and that's because if we take images while we're moving, it's gonna be more blurry and harder to process. So I guess what you would say would be great if we could just keep taking pictures while we're moving, but the thing is, we kind of have to move discreetly, we have to kind of move in steps. So I think what you're proposing would actually take longer than we think.
Or maybe stopping at a point and then taking pictures in 4 directions and stopping at each direction? Because
Yeah, that is a good thing we can look into. It's not, the turbine or fan would have to be close enough, cause it could be too far, if the fan is actually too far away, like if the fan were kind of more over here, there is a possibility we wouldn't actually be able to see this bounding box.
Yeah, cause you have an effective range on,
Yeah,
on
the,
how far you
well,
can detect it.
the drones, the quality of the drone's camera isn't, these weigh less than a phone, they're cheap, they're inexpensive. If maybe the camera quality was better, then we can probably detect it far away. So with a large commercial drone in which, there's the ability to, to have a really good, resolution, then we could probably detect things far away. That probably wouldn't work for this experiment, but with a better quality camera, we would see things farther. But with our hard cascade that we trained, we found that there was a distance in which, even though you could tell as a person, like, oh, there's a fan right there, the drone wouldn't be able to detect it.
So maybe you can follow up after the session. I mean, these are great questions. I mean, you had your hand up. I mean, if you want to go quickly.
I was just asking why you decided on a snake path and a spiral path versus various other search patterns.
We looked at a paper that already looked at different flight algorithms for searching. Those were the two that were the most effective. There was a citation on that paper. I don't know the name of the exact paper, but there was previous work already done on this, and they concluded that those were two very effective flight paths for area exploration. So we didn't just kind of think like, let's just do this. There was some paper that described the effectiveness, and then that's why we decided to use them.
By the way, this work has both application side, also the educational aspect. The way I look at it, when we use teledrone and computer vision, image processing, task planning, it has both aspects at the same time. And then I told the students, hey, we don't want to crash the big drone, because then I have to stop the whole project, so let's start with the small one, crash it to the wall, fine, we can buy another one. Okay? So that's basically how we got started. Well, let's thank Angel for his presentation.